So this is the problem. You want to find the maximum value that this blue cylinder can have if it is to fit inside this black cone, and if its axes, so the axes of the cone and cylinder coincide. So to do that we need to use optimization, and essentially we'll just start writing the basics. So a volume of a cylinder is equal to pi r squared times the height. So we're going to write this in terms of the height of this cylinder. But we need to find an expression for the height first, and that can be difficult, but we can do that quite simply by finding the angle right there, and I'll just call this x, and this can just be h. So actually I'll just draw that again to make it a bit easier to visualize, because this slant, sorry, I should probably have that in line, that this slant is always going to be the same no matter, because the height is going to change and the radius is going to change to always fit that kind of slant. So the angle will be constant while the height and the radius will not. They'll be changing with respect to each other. So we can find this angle by taking the angle from this triangle right here. So it's really annoying when your pen goes black. Alright, we can deal with that. So the height of the cone is 12 centimeters and the radius is 4 centimeters. So we can easily find that. The angle, we have 10, I'll just skip a couple of steps, but theta is basically equal to tan inverse opposite over adjacent, so 12 on 4, which is just equal to tan inverse 3. That's pretty simple. So we know that our height, which is opposite, height will always be equal to x tan theta. And we pretty much know this already from normal rules, you know, tan theta is equal to opposite over adjacent. Yeah, x is adjacent, h is opposite. It's pretty basic. So theta is actually equal to tan inverse though. So we have h is equal to x tan of tan inverse 3. Actually, it's going to annoy me if I leave that as red. But these two are going to cancel out. So we will get to the expression h is equal to x times, this cancels out to 3 because there's a 3 here, and I'll just write that nicer. That's h is equal to 3x. But x is not r, so that's a problem, but we can easily fix that. So imagine this is just the one half of the cone, because I cannot be bothered to draw the other half, I'm sorry. There. So here's your green triangle. Actually, I'll just draw in the cone first. The cylinder, sorry. So here's half of your cylinder. Now your radius is this length right there, and your triangle is here, and this is equal to x. Markers are really bad. But this length right here, this whole big radius, we know that. That's just capital R, right? Which is 4 centimeters. So R is equal to x plus the little r. So the little radius. So the radius of the cone is equal to the little radius of the cylinder plus the distance in between. And we can just rearrange x. Rearrange that for x. That's equal to r minus r. And we have the big capital R, which is 4 centimeters, minus the little r. So that's a nice thing to have. Now that we can just sub in right up here, because now we know what r is. Actually, we should probably take a little step back here. Right, yeah, so we can sub that back into our height equation, which is right here. So height is equal to 3x, but now we have 3x, so we can go 3 on 4 minus r. Really have not planned this out nicely. Sorry, I'll just write that up here. So 3 of 4 minus r. And we can just simplify that a little bit. So then we have that. So this is the height of the cone. So now we have little r is equal to little r, and h is equal to 12 minus 3r. And that's all we need to sub that back into our equation up here about the volume. So our volume in terms of the little radius, so the volume of this, actually I'll just write it in blue so it's easier to follow. The volume of the little radius, the volume in terms of the little radius can just be written as pi r squared times 12 minus 3r, which is equal to 12 pi r squared minus 3 r cubed pi. Right, so this is important, and I'm just going to rub this out so we have a little bit of space to work with. Right, so to find the maximum volume, of this cylinder that can fit into that cone, we need to find the derivative of this. So this will give us a cubic function, so it'll probably look something like that, or the other way around. Doesn't necessarily matter at this moment. But yeah, we need to find the derivative of this so that we can find the turning points. So the turning points of the volume function, because finding the turning points of the volume function will give you either a maximum or a minimum, and let's hope it's a maximum. It will be a maximum, because, yep. That was really bad reasoning, I'm sorry. But, so dv on dr, we can just apply our, usual derivative rules. So that's 24 pi minus pi r, 24 pi r minus 9 r squared pi. So the maximum will occur, or the turning point will occur, when the derivative is 0, like right up here. So 0 is equal to 24 pi r minus 9 pi r squared. We can simplify that taking out common factors, so 3 pi r is a common factor, for example. We have 8 minus 3r is equal to 0. But you can just cross out the 3 pi, because if you divide this function by 3 pi, it'll just give you r times 8 minus 3r, and this will stay 0. So 0 is equal to r minus 8 minus r times 8 minus 3r. So if r is equal to 0, dv is equal to so the derivative of the volume with respect to the little radius is equal to 0, and if r is equal to 8 on 3, because then this whole thing will be equal to 0. So this is where we have to consider the values, the restrictions of the little radius. So obviously the little radius can't be greater than the radius of the cone. So let me just write a restriction here. So the radius is obviously going to be smaller than 4 centimeters, but it is also not going to be smaller than 0 centimeters, because you know you can't have a negative radius. So we can just use these values. So v of 0, actually I should probably explain. So we can just use the values, so the endpoints, to figure out what the volume will be at those endpoints. So if the radius is equal to 4 centimeters, we can figure out what the volume is if the radius of this, the volume of this cylinder, if the radius is equal to 4 centimeters, and we can figure out the volume if this radius is equal to 0 centimeters. And obviously, it's pretty intuitive, and it will also show up in the equations. If you sub 4 into what is our equation, our volume equation? If you sub 4 into this equation, you will get 0 centimeters cubed. And that makes sense, because if you have a radius of 4 centimeters, your height will be 0 centimeters, because it will already be touching the edges of the cone. So there's no volume there. And the same goes for 0, because if you have a radius of 0, the height is just going to be right up here, and that's just you know, there's no volume in a line, at least not that I know of yet. So then we have to sub this value in to our equation. Our volume equation, sorry. And that is equal to pi it's equal to 12 pi on 8 on 3 squared minus 3 8 on 3 cubed pi, and that gives you 256 pi on 3 centimeters cubed, which is approximately equal to 89.36 centimeters cubed. And that, I believe, is the correct answer and the maximum volume that this cylinder can take on when it is placed in a cone and has to be touching the edges of that cone. So, yes, we are done.